Okay, so today we're going to solve this problem. We have a set A, which is a sequence x1, x2, x3 going on, and then we're unioning this sequence with its limit point x. We're assuming the sequence converges. We're unioning with its limit point, and then our claim is that A is a closed set in RD with the standard topology. Okay. So to show that A is closed, what we really want to use is the sequential definition of a set being closed. Okay. So this is what we need to show is that any convergent sequence in A has a limit point in A. Okay? So if I take any sequence formed by just choosing an element of A, if I view A like a set rather than a sequence, because we're really viewing A as just a set of points. A is a sequence union with its limit point, but for the sake of our intuition, we just view it as like a set of points. And then I'm going to take a sequence in A. So that could be any chaotic choice of these x sub i's. I could choose, for example, x 1,000. I could choose, for example, x 1,000, x2, x771, going on and on. And as long as this sequence of choices of members of A converges, then its limit point needs to belong to A in order for the set to be closed. Okay? All right, so let's go about proving this. Now the difficulty lies in the fact that I don't need to respect the structure of this sequence, right? I don't need to respect the fact that these indices are increasing. I can choose a sequence however I want from points at A. Okay, so let's prove this. So let y sub n be a sequence in A. That is, y sub n is going to belong to A for all n. And I actually want this sequence to be convergent. Okay, so I'm going to assume that the limit as n approaches infinity of y sub n equals y. Now the goal would be to show that y belongs to A. If we can show that y belongs to A by sequential definition of a closed set, we're done with the proof. Okay, so how do we go about doing this? Well, the first case, there's two cases I want to consider. The first case is if I write this y sub n as, if I literally write it as terms of the x sub i's sub n's, then I want to consider whether or not one of these elements is going to appear infinitely many times. Okay, so since y sub n belongs to A for all n, we can write y sub n is going to be equal to x sub I sub n for all n. Okay, sum I sub n. Now I sub n could be one of two things. So I sub n could be in the natural numbers, right, corresponding to a choice of element in here, or I sub n could be x itself. So I'm going to label x with the label infinity, and then just say I sub n could also be infinity, which corresponds to choosing the limit point here, okay? Okay, so yeah, so the ideal goal would be to show that we can pass to a subsequence. We've assumed that y sub n converges, okay? Therefore, any subsequence will also converge to the same limit point, okay? So if I can find a subsequence of these y sub n's that converges to a point in A, I know that the original limit must be a point in A, okay? So that's going to be the goal, is to pass to a subsequence. Let's write that up. Okay. So just y sub n is going to be x sub n sub, or x sub I sub n, where I sub n is within union infinity for all n. And okay, so since y sub n is a convergent sequence, any subsequence will converge. Any subsequence must also converge to the same limit point. Okay. All right. So that tells me I have some freedom to manipulate this sequence of x sub I sub n. So it might be super chaotic to begin with, but hopefully by throwing away bad x's, we can create a sequence which we can say something good about. Okay. So for example, if I had the sequence x1, x2, x3, x5005, x4, x5, x672, x6, etc. You kind of get where I'm going with this. So this sequence might look a little bit crazy, but if this is my y sub n, I can throw away the x5005 in a subsequence, and I can throw away the x672 in a subsequence and just pass to a subsequence that's, y sub n sub k, which is just x1, x2, x3, ... And this thing is going to converge to x. And since the original sequence converges to y, and the subsequence converges to x, but the subsequence also has to converge to y, because the subsequence has to converge to the same limit point as the original sequence, we're going to conclude that x is equal to y. Okay, so that's not rigorous. This is just kind of an intuition of what we're doing here. All right, so the first thing I'm going to deal with is if there's a recurrent index. So suppose that I chose, let's say, x sub 3 infinitely many times. Then I could just pass to the subsequence x sub 3, the constant subsequence x sub 3, and it would converge to x3, and I'd be done. Okay? So if there exists an I sub n, if there exists a k in the natural numbers, union infinity, could also be infinity, such that I sub n is equal to k for infinitely many n, okay? Then that corresponds to a specific point of A showing up infinitely many times in the sequence. Then choose the subsequence y sub n sub k is simply equal to x sub k. I guess, sorry, my notation is really confusing here. Maybe this should be n sub j to be more rigorous. Okay, sorry, let me just make this. This k is not supposed to correspond to this index k. So let's maybe make this a capital M here. Okay. So, point here is that if there's an index that recurs infinitely many times, then we can pass to a subsequence that's just that constant point. So this subsequence is going to look like x sub m, x sub m, x sub m, right? Because x sub m occurs infinitely often. So pass to the subsequence where we just choose the x sub m infinitely many times. And this is going to converge to x sub m, which is in A. And so we conclude that since the limit of the subsequence has to be y, because it has to equal the limit of the original sequence, we conclude that y is equal to x sub m is in A, as desired, okay? So, and I'm going to call this a recurrent index. So if an index is recurrent in the sequence, then we pass to the constant subsequence and we're basically done. Okay, so if there's no recurrent index, so if this statement does not hold, okay, then essentially I have the negation of this statement, which is if for all m in infinity, I sub n equals m for finitely many n. Okay? Then I claim that we're always going to be able to pass to a subsequence which increases an index. Okay? So then there exists a subsequence x sub I sub n sub k, okay, where k is running from 1 to infinity, such that I sub n sub k is going to be less than I sub n sub j for all k less than j. Essentially, this is an increasing, this index is increasing with respect to k. So in particular, this is a subsequence of x sub n, not just a subsequence of the y sub n. Okay. So why is this the case? Because, okay, so to see this, we note that the above statement that no index is recurrent is equivalent to I sub n less than or equal to m for finitely many. N, fin n, okay? So for any fixed m, there's only going to be finitely many n such that I sub n is less than or equal to m, okay? And so eventually, since it's an infinite sequence, we're going to be able to find an index that surpasses any fixed number, which allows us to build inductively a subsequence which is monotone increasing in index. Okay, so let's write this. Okay, so suppose for all m okay, so we're starting with x sub I sub n. This is my sequence y sub n. Okay, and I'm going to build a subsequence y sub n sub k, which is going to be x sub I sub n sub k, which is increasing in index. I sub n sub k, right? As k increases, this index needs to increase. How do we do this? Well, we just choose y sub n sub k plus 1, okay? Or I guess I should just say n sub k plus 1. So I'm going to choose n sub k plus 1 such that I sub n sub k plus 1 is greater than I sub n sub k. Okay, this is precisely, okay, so given n sub k. This is precisely the condition that I need to build the subsequence which is increasing in index. And this follows directly from this claim that nothing is recurrent. Why? Because if I fix an n sub k, let's say I start with some n sub k in my subsequence, okay? The next index of the subsequence, okay? The next index of the subsequence is going to be chosen such that when I pass to the labels on x, I sub n sub k plus 1 is greater than I sub n sub k. This is possible because there's only finitely many n sub k's. There's only finitely many n such that I sub n is less than or equal to m, okay? So this is like the negation of this statement. We're guaranteed to be able to choose this n sub k plus 1 because there's infinitely many choices and only finitely many choices which prevent us from finding an I sub n sub k plus 1 that's greater than I sub n sub k. Let me elaborate that because that is maybe a little bit confusing. Okay, so since I sub n, okay, is less than or equal to I sub n sub k, this is a fixed number that I've already chosen because I've already chosen an element of my subsequence n sub k. This is a fixed number, and this is only less than or equal to I sub n for finitely many k, finitely many n. So I can always find an n big enough, or some, because I have infinitely many choices, such that, you know, I sub n sub k plus 1 is bigger than I sub n sub k. All right, hopefully that makes some amount of sense. Okay, so finally, I claim that we're almost done now, because now I've constructed, okay, so this allows us to construct, to build the above subsequence, okay. So you've built an above subsequence which is increasing in the index with respect to x, okay. So this is x sub I sub n sub k. But notice that because it's increasing in index, okay, because this sequence is increasing in index, it's actually a subsequence of x sub n. So this is a subsequence of x sub n because it's increasing in index. It might look like, you know, x3, x5, x15, x100, etc. The point is that it's increasing in index. So it's a subsequence of the x sub n, which we know converges to x. Since this is a subsequence of a convergent sequence, it must converge to the same limit, namely x. So this also converges to x. So that proves that y sub n has a subsequence, y sub n sub k, which converges to x. By the uniqueness of the limit, the sequence y sub n must also converge to x. Since the sequence y sub n converges to y, we conclude that y equals x, namely that y belongs to a, okay? So this tells me that, okay, so since y sub n sub k which is equal to x sub I sub n sub k, converges to x, and this converges to y, since it's a subsequence of a sequence that converges to y. Conclude that y is equal to x, which belongs to A. Okay, so in either case, we've proven that the limit of our convergent sequence must belong to A, and that proves that A is closed.